Hello AP Physics 2. This is going to be the solutions video for the fluids questions you see above, 3, 11, 13, 17, 23, 25, and 35. I'm going to do this in a series of videos just in case something goes wrong with the sound or just so you guys can skip through the videos if you think you're comfortable with some of the previous ones, you got the answer right and you think you know what to do. I will probably do 1 or 2 questions per video, and they'll all be in the title, so you guys will know well before I do how everything looks and how it works out. So in this first video, we're going to go through questions 3 and 11, and then we'll move on to the next video. Let's jump right into it. If you have your homework questions, have them out while you watch this video so that you can see what you did and how it may or may not be different from what I do. Just a quick note before we do get started though, if you guys found that you're having problems getting started with the questions, and I think that was an issue that some people were having, a place that I recommend to look for is the example problems in the chapter. A lot of the times, the problems that they ask you to do in the problems section of the book are very similar to questions they already go through in the chapter. So if you're finding you're having problems getting started, look at the actual example problems in the section. That should help you at least put something on the paper and get going. It might not get you all the way through because the problems aren't exactly the same, but at least point you in the right direction. So let's go ahead and let's get started with question 3. So question 3 is a pretty straightforward one, pretty simple. There's only one key concept we need to know to be able to answer it, but let's read the question. Question number 3. If you tried to smuggle gold bricks by filling your backpack, whose dimensions are 54 centimeters by 31 centimeters by 22 centimeters, what would its mass be? So at the end of the day, we are trying to find the mass of your new backpack that is full of gold bricks. Well, surprisingly, gold is pretty dense. It's pretty heavy, so we're going to find that's actually going to be a weighty backpack. But we're trying to find the mass. Like many of the questions, there's something you already know about they tell you a given right off the bat. You're trying to smuggle gold. Since they're telling you you're trying to smuggle gold, you can know the density of gold. This is a quantity that we can always know for all the problems that we do. And it tells us that the density of gold is 19.3 grams per centimeter cubed. Now the problem doesn't tell us that. There is a chart, there's a table in the textbook that tells you that. Most of the time you'll either have to look it up in a chart or a table, or it'll be given to you in the problem, but if it tells you it's gold, you can know the density. That's something that's going to be useful all over. Something else we actually know the volume of your bag, and that is 54 centimeters by 31 centimeters by 22 centimeters, which gives us a total volume of 36,828 cubic centimeters. Now notice the units we chose. They gave us centimeters, 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 and centimeters, so we got centimeters cubed. We chose the unit of density that is in centimeters cubed to make our lives easier. So the only thing you need to know for this problem is that the density is equal to mass divided by volume. So if you want mass, it's just density times volume. That quantity is going to be useful to us in later problems as well. So we're going to hang on to that. Now we want to find the mass. Mass is equal to density of gold times our volume, which is just equal to 19.3 multiplied by the 36,828, which is equal to 710,780 grams, or 710.8 kilograms. Now you may get slightly different numbers depending on how you round, but as long as it's around that quantity, you're all set. That is a heavy backpack. That is not something you would be looking forward to lifting, or I don't even know if you could lift that. That is really heavy. So let's move on to question 11. Question 11 asks us, A, calculate the total force of the atmosphere acting on the top of a table that measures 1.7 meters by 2.6 meters, and B, what is the total force acting upward on the underside of the table? So in question A, or in part A, it asks us to find the total force. This is another one of those questions where we have to know just one simple rule or equation, and that's going to get us our final answer. So we're looking for the force, and they tell us the dimensions of the table. That's going to get us our area. So the table is 1.7 meters by 2.6 meters, which is equal to 4.42 meters squared. So we know the area. It also tells us that the force is being exerted by the atmosphere. Since we have a force in an area, we should be thinking pressure. So the pressure of the atmosphere is 1.01 times 10 to the 5th pascals. We need to make sure we're using units of pascals because our area has units of meters. Anytime you see meters, you should be using pascals. And remember, a pascal is a Newton per meter squared. So one atmosphere is 1.01 times 10 to the 5th pascals. It is also 1.01 times 10 to the 5th newtons per meter squared. So we need to make sure our units match up there, and they do now. So to solve this question, we know that pressure is equal to a force divided by an area. So in order to find force, we just need to take our pressure multiplied by our area, which is 1.01 times 10 to the 5th multiplied by 4.42, and our force comes out to be 4.46 times 10 to the 5th newtons, or close depending on how you round. So that is the force exerted by the atmosphere on the top of the table downward. But why doesn't the table go crashing into the ground? Well, because the bottom of the table has the same area and the atmosphere is exerting the same pressure upward from the bottom of the table. So for part B, it is also 4.64 times 10 to the 5th newtons upward on the bottom of the table. And the table is getting squeezed by the atmosphere, not pushed around, but compressed. So it experiences the same pressure from the bottom because it's also at atmospheric pressure. Please tune in for the next video for questions 13 and 17.